Hello and welcome back to this low-level JavaScript series where we're attempting to build the world's first hardware actual CPU running on an FPGA, RISC-V, built in TypeScript. Now at this stage we're still actually building just an emulator, and the emulator is going to serve as a sort of conceptual model going forward so that we can work out all of the hard parts of kind of how the processor is going to work, kind of in a low-level way, in a sort of low-level hardware-ish way as much as is possible, without having all of the complexities that come with actually doing stuff on FPGAs, because that's hard enough in itself, and it's kind of nice to be able to tackle those two things kind of individually. And this also gives us a nice chance to just get into RISC-V and kind of analyze the instruction set architecture and maybe even get familiar with the tooling at some point. This emulator is going to act as our sanity check, and it's going to allow us to run real RISC-V binaries in exactly the same kind of way that they would be running on the hardware, and then we can sort of run those same binaries and check that everything is kind of looking good. So there's actually been 2 episodes already of this, not including an introduction video as well. And in those first 2 episodes, we were working on the emulator, and we kind of got up to the point where we had emulated sort of half of the pipeline of the CPU, as well as like the register file and some different memory devices and kind of a system interface that does memory mapping so that when we read and write from certain addresses, that ends up going to things like a ROM device or a RAM device or any other kinds of devices that we might use. And in the last episode, we kind of got like most of the computation done in the ALU to actually run 1 instruction, or actually 3 instructions. So we're able to now run at least the addition style instructions of the RISC-V architecture. And so if I open up this beautiful document that we're going to look at a lot, we can execute this instruction, and we can execute this one, and also this one. And what I'd like to do today is I'd like to finish out the ALU, and I would like to implement the rest of the pipeline and get to the point where we can not only execute the instructions and compute a result out of the ALU, but also then store that result back into a register. That sort of closes it closes the circle on the whole pipeline, and it also sort of gets one big set of instructions done, which are these ones, which is a huge chunk of the middle instructions, and it just gives us a great base. And the previous 2 videos, they've been pretty long. They were both about an hour and a half each, and I would love to go a little bit shorter with that today. So that's really my aim. I'm going to keep my expectations relatively small. Let's try and finish the ALU. Let's try and get stuff stored in registers. And if we can do that, I'll be super happy. All right, let's jump back into the code. I noticed when I was going through this previous video that I'd actually made a couple of small mistakes. One of them is that somehow I managed to, I wrote this, but then I overwrote it instead of copying the line and moving on from there. So I've actually, this enum now does contain the actual 8 operations. And I noticed one more problem, and this is one that's just like I'm going to make all the time. And that is that instead of writing to ALU result next, I wrote to ALU result here. And it's funny because when I was doing the testing of this in the end, I should have seen this. I should have seen that this was a problem then, because I checked the result immediately before it had been latched and it was already there. And that's of course doesn't make sense, but it's easily fixed. We just do that. If none of this is making any sense to you, then you either haven't watched the initial videos, in which case you should probably watch the initial videos. Then it will allow you to make some more sense of this, or otherwise. Maybe you're going too fast through the material. You should go back a bit and just Google some of these terms, read some Wikipedia pages, and you'll kind of get up to speed, I promise. Otherwise, leave some comments, and I'm happy to answer questions if I can. All right. So actually, add now. I consider this to be done. I'm not sure if I want to start with finishing off the pipeline or if I want to implement the ALU instructions first. And I think what might be nice is kind of get the pipeline done, because then we can sort of test these first instructions, and then we can go and just sort of bang the rest of them out all in one. So let's finish up the pipeline. We've implemented the instruction fetch, the decode, and the execute so far, although all of those stages are sort of incomplete because we need to implement the entire processor for those to really be complete. I want to rename this the instruction decode file. I want to rename it decode. We don't need the word instruction in front of everything. So I've done that, just need to save this file. That's all good. Let's save that. So the next stage, so we have we have memory access. And for now, we're not going to do anything with memory access, although it is should be a fairly simple stage. Let's use decode as the basis. That's kind of weird. Alright, just took a few times for the keyboard to work there. Memory access. And yeah, every time we have the word decode, let's call that memory access. And we don't need that. We're just going to delete a whole bunch of stuff here first that we won't be using. Yes, let's get rid of those. Let's get rid of everything in the compute. Let's get rid of everything in next. And we don't need this method at all. Alright, so now we're in a sort of like more or less empty state. So we need this should stall signal. We're going to need to get the ALU result. And we're going to need to get the destination register because we need to know where we stored this thing. Yeah. Oh, we're doing memory access, right? So what we need now is we don't need the ALU result, although we do because we need to bring it in and basically pass it along. Like we sort of don't care about the ALU result here, but we do want to take it in and pass it on. But what we want, really, I guess the way I'm going to do this is I'm going to say get execution values in, because I like the idea of just having one function to bring everything in from the previous stage, rather than a million functions to bring in a million different things. So we don't have a type for this yet, so I don't know, I'll call it null for now. And in execute, right now we're just going to pass on the ALU result. So I called it get ALU result out. That was really only for testing. Let's just call this get execution values out. And yeah, maybe that's return an object already, so we can start thinking about doing this. So we can return an object with an ALU result, which is this. It's pretty okay. Sounds good. One of the things we could do, I was playing around in the decode stage, especially, right? We have this get decoded values out, and I made this type to reflect what that method actually returns. And this is not strictly necessary, actually. And I'm just going to prove this to myself by taking this out. I know I'm doing multiple things at the same time here, so I do apologize for that. But I just kind of want to get this all straight. So here we have this decode stage, and instead what we can do is we can use some TypeScript sort of magic here to get the return type of decode, and then we can introspect like its inner value, and then there's this get decoded values out. So if we do this, then this actually now knows, like, if we sort of were to analyze this, well, in any case, it knows what we get from this. So if I do this here and we look at decoded, it's going to understand what these values are. And that's kind of nice. It means we don't have to repeat ourselves, but it also means that we don't need to like keep a separate type around and use that type. We can sort of like talk about that type being reflected from the method, since it's just more useful and less likely to get out of date if we end up returning more or less values from that thing. Like, we won't have to change two places. So I want to do the same thing here with execution values. So I'm going to, in memory access, we'll bring in, what we'll say is that this is the return type of execute, and then get execution result values out. So we need to bring in the ALU, but we're also going to need this address. So we need to kind of figure out how we're going to compute the address. And yeah, I'm wondering, is it worth, like, actually for now I'm not going to do any implementation of the only thing I'm going to do is I'm going to like buffer up the ALU result, and I'm going to pass it on. I'm actually not going to do any of the memory access stuff, like computing any addresses or anything. We'll do that when we get to the load and store instructions. So private ALU result, and it can just be a number because we are just we're just going to bring it in and pass it along. And then we'll have this, this is going to be get memory access values out. And then here we'll just end up returning ALU result, this dot ALU result dot value. Oh no, we don't have registers, so we don't need to do that. Good. This dot ALU result. This right? No, this is not right. We just need to get this equals params. That's kind of weird. Oh yeah, it's kind of verbose. Like when you're passing in, we're sort of, what we're doing here is we're like passing in methods. We're sort of borrowing them from other classes almost. And so you actually still have to say, yeah, like this is a property on this thing, which is get execution values in, which is like has the type of memory access params get execution values in, and then we can assign it. And then here in compute, we're going to say this dot ALU result next is going to equal this dot get execution. Let's do this for const execution values. Kind of generic, but it will work. Get execution values in. Here we should have our ALU result. So that's pretty simple. And then here in latch next, we just want to say this.ALU result next. That's it. That's kind of the barest of bare bones that we can do in this stage. Let's move on to the last stage, which is write back. Yeah, and of course these get execution values in, I actually want to pass on more than this, right? Because I want to pass on a bunch of the stuff that we get out of decode, which means we're going to have to store a bunch of stuff from decode. What are we going to want to store? We're going to want to store RD. That's like RD is going to be a number. So yeah, that was something that I should have done in the memory access. here I typed these two things as numbers, but instead what I should do is just assign a default value, and then it knows it's a number and it has a valid value. Let's close some of this. Cool. We want RD, we want RD next. And when we do this.decoded, we're gonna also, let's just put this straight away on this.rd next. It's gonna be decoded.rd. And what else do we have here? Do we need, is there gonna be anything else needed here? I don't think so. I guess we will need some sort of selector to know, like, are we going to choose the AOU result, or are we going to choose like what came back from memory, because that will also be something, or are we going to choose some sort of immediate value, because that also happens. And for now, it's simple for us to say whether or not, like, No, let's just refine that when we get to it. So for now, I'm just going to pass on RD. Down here, we can say RD equals this.rd next. And that's one of the things we will pass on. Cool. That works for now. Let's hook up the execution stage, the memory access stage. So we'll call that mem. It's going to be a new memory access, and that's going to take some parameters, one of which should stall. And in that case, we're simply stalling if we're not in the memory access stage. And the get execution values in. Doing this whole bind thing, I just want to check something here. I want to see if I can do this dot x dot get. Yeah, I prefer this. So let's do that for all of these. There are two function calls being made here now, but like, that is fine. I think it just makes more sense. And I'll make that uniform at some point, that we call this get instruction fetch values out, but we genuinely only pass one result out here. Okay, so that's mem. We want to do it that we compute its value. We want to latch its value, and we also want to include the idea of going to the memory access stage. And if we're in the memory access stage, well, we're going to go back to instruction fetch for now, but we're just about to implement the other one. So that was memory access. And the last stage is write back, where, surprise, surprise, we write back to the registers. So we're not going to need execute this time. We're going to need memory access. Memory access. Memory access. All right, so we're going to have that. We're going to get our AOU result. Well, actually, this is kind of a thing here. Do we need to... There is some stuff eventually when we get to the point where we're going to have like proper pipeline stalling in place. You know, at the moment, you know, we don't have parallel instruction pipelining. We just have a pipeline in which every instruction has to move through, and thus not really having any real benefit to having a pipeline, other than the fact that we've put the foundation down. That means that if we're not stalling at any moment, we can just pull in the value and use it. So I actually don't think we even need to keep any values here. Like, I think we just need to in here get our memory access values. So verbose, but we can just destructure them out of here. In fact, I might just do that now. RD. That's kind of interesting. I guess we're not passing along RD, right? We get RD out of the other one, and we also need to pass it along. So RD. Let's do the same here, right? ALU result D. RD. So write back. Yeah, so we're not actually computing or latching any values here. We're also going to need the register file here, of course. Reg file, which is an array of register 32s. Let's put that reg file. And this.reg file is barams. Pass command line every time. Barams.reg file. Cool, let's pass that in already. We don't have a write back stage yet to pass anything into. Great, so now we've got a register file, and now it's really easy for us to tell if something's an ALU operation, right? We just need to look at the opcode, and if the opcode, ignoring this bit, if the rest of the bits are equal to that bit pattern, then it's an ALU operation no matter what, right? So I kind of do want to do that. That means that we need to go back to... We're going to do this in decode. Actually, I'm just going to do this in execute, since we're already computing a bunch of stuff here, like we're pulling out RD here. Let's... I'm going to end up changing this, but I'm going to just put, this is going to be is ALU operation. And we'll make these booleans. And so this will be simple. This dot is ALU operation next is going to be the idea of taking the decoded.opcode, and then we want to AND it with, I'm just going to do it in binary because we want the first bit, we want to ignore the second bit because this second bit is actually a sort of indicator, right? So like when we're doing immediate instructions, it's 0, and when we're doing register-based instructions, it's 1. Everything else is the same, so I'm just going to ignore that bit, and then we'll get 4, 5, 6, 7. So that's going to allow us to pull 7 bits off. Yes. So we're going to say, is that equal to, we're jump to the next page. Is it equal to this? And if it is, then it's an AOU operation. Is AOU operation. Alright, so now we're passing that through execution. We need to do exactly the same thing in memory access. Again, it's kind of tedious, but here we're passing on RD next. Not correct. Kind of tedious. I know, but it's kind of the way it is, right? It's just sort of part of the game of doing something like this is just the fact that you've got so many signals. Like in the CPU, you're going to have so many signals doing control stuff, doing data stuff, like computing intermediate values, and like most of what you're going to do, or most of what we're going to be doing here, is just like hooking those signals up together and just like sort of saying where one comes in and goes here, and sort of defining module boundaries, and then like taking stuff in from a module and putting it out, and then you're going to be plugging that somewhere else. And it's like, if this feels tedious, then you kind of need to get used to it, because it's going to feel tedious when it comes to the hardware as well. It's just sort of part of the game. So is AOU operation next is going to equal is AOU operation. And we will. I just can't type today. Alright, so now now we're passing that through, and the reason I want to do this is because I just want to have some gating on whether we actually do or do not write to the registers, because we're not going to write to the registers in all circumstances. There are going to be a couple of different circumstances where we write to registers. Like if we're doing a load, then we're also going to write to registers. And if we do that, we're going to have like an is a load instruction, and then is an AOU operation, and then we're just going to OR those two things together. And if either of them are true, we're going to end up writing something to the register. So this is just like an enable signal for this module. Yeah, so we're going to want to pull out our is AOU operation, and then if is AOU operation, cool, we're going to write something, we're going to do something with it. And this is an opportunity for us to, well, if A is an AOU operation and RD is not equal to 0, because if RD is 0, then that's basically like a no-op as well, right? You can't write to the 0 register. It always has the value 0. We could allow the write to go through, because when we read from this register, we always give back 0. So we only really need to do this in one place. So, like hardware-wise, this is a waste of hardware. And so, yeah, actually, let's get rid of it. It's a choice. That's a conscious choice being made. Like the FPGA, we're going to use less resources if we do this, and we can sort of guarantee the RD. If it's 0, then we sort of don't care. Like we're never going to be able to read a non-zero value out of it. Okay, so then it should be as simple as getting the register file, plugging RD as our selector, and saying it equals the ALU result. But we have to say that the value equals the ALU result, because this is a register class, and we have to write to this value. That is it. That's it. So I'm tempted to, well, I'm first tempted to actually implement this. I think that's a good start. So this is going to be get the memory access, and now we're doing write back. So WB is new write back. To that we will pass our should stall. Write back. We will pass our register file, this.reg file, and we will pass our get memory access values in, which will be the result of calling this dot mem dot get memory access values out. So that's nice. Those two things are matching up correctly. WB, and then add our final stage in, write back. Cool. That is the, the full state machine for our extremely simplistic view. Yeah, I kind of want to try these same instructions again, and I maybe also want to try doing something slightly more complicated. So what I also want to try is like making this all ones, so that this would be a -1 instead. I think that would be interesting. In any case, right, we're always writing to R3 here. Here we're supposedly writing to R4, but we're not. And let's write to R5. So we actually write to 3 different registers. So R3, R4, R5. I'm assuming, I still don't know if this is actually how this gets laid out. Yeah, cool. Let's give this a go. I'm quite excited now. So just gonna close a bunch of stuff up here, and then just open instruction fetch. And again, this seemed like a nice way to do it yesterday. Just put a breakpoint in there and we'll follow them all through. Takes a little while to compile and run. So first grabbing our instruction, and then I'm certain that all of that works properly now. So then we get here, we can just jump out, and then we can go into decode, pulling out the decode stuff. Should be all good. Yep, that's our register value, like one of them. So again, then we get to our execution stage. And let's jump in here. Immediate 32. We get a 1 there. Is this an Aou operation? Good chance to check. It is. That's nice. We're going to run through here. So we're going to say, is this a register operation? It's not. And so this time we're actually writing to the correct thing here. So we're adding 1 to that whole situation. And then we're breaking. We come up. And at this point, this is a good moment to check, like when I did this, the execution, if we get the execution, where is this now? Get execution results out. And then Aou, that's interesting because Aou result, no, it's not interesting. It's exactly what it should be. Getting confused here myself. And then now we've done the latch, so let's run the same thing again. We see it there. We do Aou results .toString 16 .pad start up to 8 characters with zeros in the beginning. Yeah, that's perfect. We've added 1 there. Awesome. Okay, let's see if we're able to write it back. So now we're going to end up back in there again. We'll jump out. Maybe it makes more sense to put a break here, but just not do that. So then we did our. Now we need going into our memory access stage. So we're pulling these values out. We're simply assigning them to another set of registers and passing them on. It's a very, very uninteresting situation. And then we get to the write back. So then we're going to jump in. We should stall. So we get these 3 things. So things to check here, right? We're supposedly outputting to R3. So let's see. RD is 3. Perfect. This is an AOU. That's interesting. So I bet I messed that up in the... in this part, like with the latching. And of course I did, because we compute the value, but we never latch it, which is kind of important. Oh, typing, so hard. But we do pass it on, so that's good. Alright, so let's refresh this again. And what we can do is open up the write-back stage and put a breakpoint in here. Temporarily remove this one and just skip over all that stuff that we've seen working. So now it is an AOU operation, so that's good. We're going to come in here, we're going to write to the register file. Boom. And so that's interesting. I'm actually thinking now, yeah, this is something to is it something to think about? Yeah, I think I think we're actually going to need like a secondary register file. Because if this stage, I guess it doesn't matter because it's going to be the last stage running, but like this whole thing that we have with a compute and a latch, what we're actually doing now is like in one of these compute stages, we're like writing to something that could be immediately visible to one of these other stages, and that shouldn't happen, but it sort of doesn't matter because it's the final stage. But because of stalls and stuff like that, that can be a problem. So I'm going to make a sort of mental to-do note here that that we need to clean that up. Like we need to have basically a copy register file, and I think what I'll do is I'll end up making a special register class that you also have to call latch on, and then we can just have one register file. We can write stuff to it, and then we have to call latch in order to take on the new value. So it will be a sort of, you know, and we'll just sort of fractally implement this compute and latch next thing all the way down. But this is great. I'm quite happy with this. So let's just get to this point and let's read into this register file, this.reg file. And we want the one at index 3. We want to get the value. We want toString 16, and there we go. We're missing the first 0 because it chops it off, but 0, 1, 0, 2, 0, 3, 0, 5. That's so cool. I'm so happy with that. Alright, and yeah, so now we can try this out with the other ones, and let's just also skip over everything and let's jump straight into the write-back stage again and assume everything is going to work correctly with the decoding and the fetching and everything, and if it's not, then we'll investigate it at that level. So what we should have is a destination of 4. We should have a true here as well. Here we get a false, so that's interesting. So I guess the way I've done this like anding off with the opcode is not correct. That actually happens in the execute stage. So let's put that down here. Let's make sure I am writing that here. Do a refresh. So it's going to catch in here first. But this is the first instruction. We know that actually worked. That one is true, but let's run this again. Then we get here, and the opcode this time, well, let's just look at it like toString 2.pad start, and this is a 7-bit thing, so let's pad it up to 7 characters. Is that right? It doesn't look right to me. It looks like... so we're doing an add, right? So it should be this. But somehow it's this. And that looks just wrong. So, yeah. I'll just throw this in there. So somehow, like, is half of any of that right? I feel like we're like off by 1 somehow with this. Something to check. We are getting 7 here. Like, well, this is wrong. The opcode is wrong, which means we're decoding it wrong. How can that be? If it decodes the other one correctly, I don't understand how we can be wrong here. But let's do this, right? Let's do decoded.instruction. Take a look at the instruction, toString 2.pathStart to 32 with zeros. Yeah. So the whole instruction just seems like off somehow. Yeah, so it doesn't make a ton of sense to me, this. Like 2 zeros at the end. These opcodes are just messed up somehow. I don't understand how we've gotten into this opcode situation, because I guess that's just me, right? I just messed this up. I really hope it's me. Because, I mean, this is what it should be, so let's just paste that in and make sure it's the same. Okay, so apparently I've just made a stupid mistake there somehow. Alright, so that's instruction 1. This is instruction 2. And this time it's true. So that is a relief. Alright, let's get to this point. So we have register 4. It is an Aou operation, and we have a result. And I'm going to like compute whether this result was correct in the first place. So what we're doing now is we're adding 1, 2, 3, 4, but not 1, 2, 3, 4, because this is now a 5, because no, that's not true. We haven't overwritten register 1, so we should see just the natural thing come out of this. Where are we? We're in right back, right into it. This.reg file, forward toString 16. Yes.value. So we get 3, 5, 7, and 9, and that is indeed the expected value. Let's get here one more time. It's also an Aou operation, relief. Although this time RD is 4, and that is not correct, right? I think I edited. Now I know what I did, right? I edited this thinking that this was the destination register, but of course this is the destination register. So this was completely my own doing, and I'm sure people at home noticed that. So I deeply apologize. Cool, but then that's fine because that is the expected place we're writing to. And now we should expect 0, 1, 0, 1, 0, 1, 0, 1, which we get. Perfect. All right, and just for a little bit of, being diligent, let's try to execute a sort of like 2's complement subtraction using add I, because we can do that. 1, 2, 3, 4. 5, 6, 7, 8, 9, 10, 11, 12. So that is our 12-bit minus 1. And we can just comment those out. Doesn't really matter, but... So what's going to happen here, right, is that we're going to sign extend that 12-bit number, which means we're going to push basically 32 ones. So we're going to have a number that's just all Fs, and then that should do a subtraction, and what we should see, instead of it being 01, 02, 03, 05 like it was with addition, it should be 01, 02, 03, 03. If all goes well. Let's try that out. Break here. So RD was 3, I believe. Can't read that anymore, but let's take a look. That's interesting. That's not what I would have expected. 01, 02, B0, 3. Something went wrong there. But that's interesting. Let's see where that happens. It's got to be at the decode stage. So let's go back to decode, and let's put a breakpoint down here when we've decoded a bunch of these values. Alright, so our immediate 11, so that looks about right? 2047, that's one bit off being 2048, which would be a power of 2. So this dot in 11 next dot toString 2 length 11 bits. Well, that's not correct. It's not 11 bits. So did I miscount? I'm pretty sure I put 12 bits here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I did put 12 bits. So I guess I'm incorrectly pulling 12 bits off this thing. 7FF should pull 12 bits off. Is shifting down by 20 bits correct? I would have thought that it is. So is our 12 bits. We're at bit 20, so we're going to shift down by 20, which should leave us. So let's take a look. Let's just take a look at the instruction, shift it down by 20. Read that in binary. Got toString. Because actually we don't need to mask anything. If we shift down by 20 bits, like there's nothing coming in on the other side. Like as long as we use logical right shift. I also apologize, if you watched the last episode, I called logical right shift arithmetic right shift so many times in that episode, which really frustrated me watching it back. But yeah, I was cringing because I feel like, oh no, why am I'm giving the wrong message here? But yeah, it's logical because it literally for the fact that it's not arithmetic, you know. We're not using it for arithmetic reasons. Okay, so if we make this a 2, and then we see a bunch of stuff there, and then we get length, and the length is 12. And it's just kind of, yeah, it's kind of strange to me because I would have been kind of certain that this mask would have given us 12 bits. But I guess it's an 11-bit mask. So, yeah, that's kind of. Does that make sense? Yeah, I guess it kind of does make sense because yeah, no, of course it does, right? Because 7 is 3 bits, and then F is 4, and then F is 4, so it doesn't add up. We don't need to do the masking, but I would, you know, the correct mask here would just be FFF, of course, right? Because we get 3 groups of 4 bits, so FFF. I'm going to put it in there just so we don't need the mask, but I'm putting it in there just for the sake of it. So then we should have 4096. Okay, so we're up 1 power of 2, so that seems correct. And let's let this jump down to the right backstage now. Because I would have expected that to actually now sign extend to a correct value. So we write into the reg file, and let's look up the register, and we see 01, 02, 03, 03. That looks good to me. And All right, I think we're at 49 minutes in. That's not like too short of an episode, but I'm pretty happy with that. We have all 5 of the pipeline stages implemented now. It doesn't matter that memory is doing, not doing the right thing. It doesn't matter that execute is also missing a bunch of its functionality, and that write back is, of course, just writing back only on Aou operations. This is a great start. And I'm really... Oh, well, actually... I'm getting ahead of myself because it took all this time. I actually wanted to implement the ALU, so I started to end the episode there, but I think I'm just going to go back and implement these things because I don't think it will take too long now that we have the basis for it. And we're sort of already going, so let's just finish up some of these operations. Okay, so what's the next operation that we have? So that would be, so this one is, so shift left logical, SSL, and we have our shift amount built in because let's go back to page 104 where we have our instructions. So shift left logical is a register operation. So our shift amount is inside RS2 and the register to be shifted is RS1. So shift left logical. We don't need to check if it's a register operation because it just is a register operation. Oh, that's not true because this just encodes the idea of shift left logical. So it could still be, right? We just have this thing, but up here we have shift left logical immediate and it has the same function. So we do need to check if it's a register operation. Shift left logical doesn't have an alternate, whereas shift right does have an alternate because it has arithmetic shift, but there is no arithmetic left shift, of course, because like arithmetic shifts relate to the sign bit, and if you're shifting left, you're not shifting the sign bit down. You're shifting the sign bit away. So it doesn't actually even make sense to have an arithmetic left shift. So we're not going to have an alternate in that case. So we'll just ignore alternate, and we'll simply say this.rs1 is going to be left shifted by this.rs2.value. Probably need to use .value in these cases. Decoded.rs1. And we're going to need to wrap this up RS2. We're going to need to wrap this up in a in a twos because we could easily get a we could easily end up with a thing here. And let's also do this now because we just have one level of one level of if statement here. So let's turn it into a ternary. If it's a register operation, then we'll do this one, and if it's not, then we're going to use this this shift amount, right? On the immediate instructions like this, we have a shift amount which would have been encoded into which would have been the address of RS2 basically. So decoded.shift amount. So then we can get rid of these if statements, and that just becomes this. That's easy. Okay, next one, ALU operation. Next thing, like sequentially, is set less than. That's also kind of easy. So this is a register operation. This is an operation that is comparing like two values, and it's comparing those values in a signed way. So we're doing a signed comparison here. So this is one of those rare times where we don't want to like do away with JavaScript's weird interpretation or like reinterpretation of 32-bit integers. We want to do untos. So if our number is going to be greater than 0x8000 with 4 extra zeros afterwards, then we're going to actually do a 2's complement flip on it. And if it's not, we'll just return it. So because in this case, this means it's negative, and here we want to do our like negative flip to turn it into an actual signed JavaScript number. Wait, is this correct? What we want to do here, right, is... No, if this is the case, the simpler way of doing that is just to take advantage of what JavaScript's doing and doing this. So we're flipping the bits, and then we're flipping them back. And then that should have the result of turning this into a thing. So let's just try it out. If we've got, and also this should be less than or equal to, we've got a number like OX8004, and we do like this. That looks good. So if we did that, yeah, perfect. That is excellent. And if we said A is OX FF, we say Shift A, we get -1. Perfect. All right, that's cool. No ternary here. I was tempted to do it, but I'll just leave that for now. So we had set less than, right? And it's going to be like this, although we're not going to have any alternates, so that's also useful, right? There's no alternate version of this. We have set less than, and we have set less than unsigned. And because there is, because we have two versions of this, also for the immediate, there's no way that that is encoded. So these are two separate operations. So set less than. If it's a register operation, it's kind of funny, right? We're doing like this. We're not shifting them. We want to say, oh, we need to cast this back into a number. This is getting a little bit hairy because this is, of course, we need to untwo's both of these numbers. Untwo's. In hardware, I'm going to be smarter about this because, like, what you're going to see is that we don't need to untwo's so many different cores here. We need to pull this out. Untwo's is by the way not a name that anyone actually uses. It's just something that I've decided makes sense in this context. So we don't want the shift amount there. We want to check the immediate 32. Yep, that looks good. Then we break. Right, because well, we're doing yeah, it's fine. It's fine. No point in getting too fixed on it. So we have first set less than, then we have set less than unsigned. So let's do that immediately afterwards. And the difference here is we simply don't need to untwo's these numbers. So we don't need those at all. And the automation. Okay, I think that should work. Next, what have we got? Let's just keep blasting through this. We've got XOR, nice and easy. XOR, if it's a register operation, we're gonna do some twosing here. Like we're gonna like re-twos our result here, because when we XOR we might get weird stuff going on. You can see that like once you've got like the basis set up and you've sort of done like the adding is the most, the trickiest one, but once you've kind of done a few of those, you're just changing the symbols every now and again. It's a little bit, you have to do a little bit more work with the signed and unsigned stuff, but not too much. So after XOR, we have shift right logical. So let's just copy shift left logical and paste that in. And logical, of course, uses our 3 symbols. Still need to think about choosing it. Do we need to think about choosing it? Because that's kind of the point, right? If we are using a logical shift, that is the one operation that is not going to matter, because if we had a 1 in the sign bit, we're shifting it away anyway, and we're going to bring in a 0. So actually don't need to do this part, which is nice. Whatever. Trying to get fancy with keyboards, not worth it. So that needs to be shift right logical. Shift right logical. Then we have OR, very similar to XOR, except we use a different symbol. Great. What's next? And that's the last one as well. That's it. That's the ALU. And that is pretty much exactly how the ALU is going to look when we implement it in hardware as well. Except there, of course, we're not going to have all of these. We won't have all the calls to twos and untwos. We'll have to be a little bit smarter about how we do signed and unsigned comparisons. Although I have built something into Gateware TS that deals with signed and unsigned. So there is something in like the language that Gateware TS compiles down to, which is Verilog, which has a function there to interpret something as signed when you're doing a comparison. So it just gives a bit of information to the compiler, like, hey, I'm doing a signed comparison here between two numbers. And then it can turn it into the right kind of hardware. Because, of course, what you need to do is you need to do your comparisons slightly differently, because you need to take into account the sign bit and then do some flipping around and making sure things are all right. But yeah, I think I'm not going to sit here and test all of those. Maybe I'm going to test like one or two of them now. So let's just try a shift right logical and a shift right arithmetic, and let's put two of those in. See how that looks. So yeah, we'll just go back to the integer computational instructions. I guess we don't actually need to do that. We could do it from page 104. So what we're going to do now is shift right logical. So this is the basis for that. So we have in the beginning, let's go from this direction, it's already here. Register 2, so we're doing this as a register operation, so we're going to put something in register 1. I'm just going to put this number in there, because then we just have a 1 all the way in the 31st bit. 32nd bit, thinking of zero index. So that's RS1, and the shift amount, let's just make it 1 for now. So it's just like, really simple. So that's going to be in RS2. So RS2 is our shift amount. 1, 2, 3, 4, 5. And RS1, 3, 4, 5. That's going to be the thing. We have 101, and our destination register, let's put it in R3. 2, 3, 4, 5, and then we have our opcode. Alright, let's just run these one at a time, and what we'll do is just put this here. So that's instruction fetch, decode, execute, memory, write back. Let's look at what is going on in register 3. So rv.regfile 3 toString 2.pad start up to 32 with zeros every time. Now it's telling me RV is not. Oh, it's because we're here. That's fine. We can use this. And also I forgot value. This dot reg file, and then we need to grab the value. See how that ends up looking. That's perfect. We've shifted one bit across. I don't know why I didn't expect that to work somehow. All right, if we put that one bit on here, that should turn it into an arithmetic shift. Did we implement arithmetic shifts? I have the feeling that we didn't end up doing an arithmetic shift somehow. So this was just like, I guess the problem is that this is not shift left logical. This is shift right. This is just shift right. And we actually do need to check the alternate there. So shift right. And we're going to check if it's a register operation. And if it is a register operation, we need to determine whether we are going to do this. So I'm going to break my little rule here and do 2 levels of ternary. So this is going to be is alternate. So that is the case where it's not an alternate. And in the case that is, we're going to want to do 2 levels of ternary. It's always a bad thing. And we'll choose that back up. Alright, so the first time around, nothing should change here, so I'm going to run it anyway. So this is 1, 2, 3, 5. Run through our 5 stages. We should see we shifted a 1. Great. And then I'm just going to flip that 1 bit. One, 2, 3, 4, 5. And what we should see is 2 1s now, because that's not right. We didn't. Oh, I probably put untwos there instead of 2. No, I didn't. So, okay, that's fun. Let's put a breakpoint in and see what's going wrong. Alright, so I'm back. It's actually the next day after I recorded this, and I sort of struggled through this problem that you just saw for a while. And I was kind of convincing myself that I could find a nice solution to it with, just using shifts and stuff. And I looked at trying to go into using something like BigInt to try and solve the problem. And I was avoiding the sort of most obvious solution, which was to basically to capture this value as a 1-element uint32 array. Because it just feels kind of wrong to create these sort of like 1-element arrays all over the place. But upon reflection, this is really going to be the cleanest way to do it. And I think my biggest aversion to it, not only for the reason that it somehow feels wrong, although for a reason that I can't really put my finger on, like, I want to say something that the performance would be bad or something, but I don't know if that is even true. So I think my biggest aversion was that I kind of liked the idea that we were doing doing the bit manipulation here, because that exposes what we're going to do on the hardware level. But I think we've seen enough of it. The concept should be clear enough by now as well for a lot of it. So I think what I'm going to do is just implement quickly a fix for this, which involves using a uint32 array with 1 element. And actually this is a good moment in this function to allow the register 32 to have like a latching mechanism, because then we can use a 2-element array, and we can just, when we write into the value, we'll write into 1 element, and when we read from it, we'll read into a different one. And then when we latch, we'll sort of like copy from the sort of one we're writing into the one we're reading from. So we're sort of having this double buffer situation that is acting as our latch. And I think that should work pretty nicely. So let's do this. So instead of having a value, which is a number, we're going to have a value, which is simply a new uint32 array with 2 elements. They'll default to 0. So if we set a value here, we're going to set, I think what we'll do is we'll say that the first element is, well, actually, I kind of guess we want to set both at this point, right? Because this is the initial value of the, somehow feels weird to set element 1 before element 0. So we'll do something like this. So we can take on an initial value here, and then when we get the value, we're going to be getting, let's say, element 1, so that's sort of like our buffer. And when we write into the element, this gets so much simpler, right? Because now we're just saying this dot underscore value 0. Yeah, this dot underscore value 0. Wait, when we get, let's get from 0. And when we're like writing into our buffer, that will be 1. I think that makes a bit more sense. And then we'll have a latch method. We'll call it latch next to match everything else. And then simply what we're going to do is say this dot value 0 equals this dot value 1. Yeah, this feels even simpler, which is nice. I like that. So then we've also got this to's complement function here. And I think, yeah, I think the way I'm going to do this is we could construct a new uint32 every time, but we're just using this as like a scratch temporary variable. So I think I'm just going to create it outside the function, not expose it to the rest of the system. So we'll just make a const, call it just to's temp, and it will be a new uint32 array with a single element. And then what we'll do is we will say that to's temp is going to equal v, no matter what v is, and that will be element 0. And then we'll simply return the value in there. And then the nice thing is that's going to happen, and this is kind of where it gets a bit black box magic-y, right, is that if we put a negative number in there, it's actually going to just automatically convert it to its proper encoding. And it's really useful. I feel somewhat defeated having to do this, but I think in the end this is for the better. Now, so then what's going to happen, right, is that we need to go and change all these places that we have registers. So where we do this, well, the nice thing about it is that if we have a register, we no longer need a next. So we can get rid of that. And that means we don't need to write into any of these next. So I'm going to rename that. I cannot rename that symbol. Let's do this. Let's get rid of that, and let's rename this symbol AOU resolve. Oh. Rename symbol AOU result. Great. Then in latch, we'll just call latch on this. Great. Yeah, that feels good, I think. All these places that we're calling to's here, we really don't need to do it because we're writing into a register, and that is going to do that operation anyway. So let's just get rid of those. We have unto's. Here we're doing to's. And here we're doing to's as well. Have some keyboard stuff that goes wrong every now and again. Alright, so that's in this stage of the pipeline. We actually have other registers in other stages, so let's just go from instruction fetch. We have an instruction here. We don't need a next anymore, so let's rename that instruction. We're writing it to the value. PC is also a register, so we also don't need a next for that, so let's I do like that this now simplifies this part of the code. And then in these cases, we just call them latch next. Yeah, this feels pretty good. So that's instruction fetch. Then we're going to go to decode. We don't have any registers here. This is also going to fix our reg file problem, and I like that too. I like that, yeah, we can latch all of the registers at the end. I mean, it might make sense to actually just have like a raw, well, I don't know. This works okay, I think. So we don't actually have any registers in this one. We just have raw values. We need to make sure that when doing certain kinds of shifts, that this is not messing up, but it didn't seem to be, and we played around with it in immediate yesterday. So decode looks good. Go to execute. In execute, we have an ALU result register. And we've already fixed this one, of course. Memory access. Here we don't have any registers, so we shouldn't have to fix anything. And in write back, we also don't have any registers. So I think we're good in that case. Then we can go into the main file. We're gonna run compute. We're gonna latch next, and then what we can do is we can iterate through the registers. So reg file for each R, and we'll just call latch next on R. Okay, I think yeah, I think that's good. So we can do a check here. This is the shift right, so we can check that this works. So that's probably a good idea. Do we have in execute? Let's drop a breakpoint in, and let's go and run this and make sure everything's right. A problem of some kind? The error. Register 32 element has any. Type 1 can be used. P1 does not exist on number. Where is the line that I'm doing this on? I seem to be getting this. It's a really unhelpful error message. But apparently I'm trying to... I mean, it's probably in that register 32 file. So what am I doing here? Here we're writing into it. I mean, this looks okay to me, I think. Let's just try running this like here on the terminal and seeing if it improves the quality of our error messages. This really great output. This property 1 does not exist on type number. Oh, okay, yeah, that's a really stupid error. But also one that can happen really easily. Okay, so let's go back to running debug, because that hopefully is the only error. Alright, so now we have a register operation. We're using the alternate. It's a register op. So we're going to shift that number down. And let's just take a quick look into what we have here. Now, there is a bit of an issue that might happen with this, and that is that I think sometimes we write into a register and then we like read its value like while we're working in the same file. And if we do that, of course, we're not gonna we're not going to be able to get its like working value. So I think we need to add an extra method there, because I think something could go wrong. That's kind of, I guess, why is that happening then? So if we read value, we get 0 here. And that is, yeah, that is exactly for this reason, right? We can't read this out. So we can get ourselves to the write back stage. So here we should have latched that value, but we can go this.x.get execution values out.aou result .value.toString2. Cannot read toString of undefined. That's kind of weird. We can't get a value here. Oh, okay, so by this point, of course, ALU result is a number. Yeah, that does make sense. Pad start 32 with zeros. Okay, so that seemed to work correctly. That's good. What I want to check is if we're in any of these stages and we have an instruction, if we're referring back to the instruction value. So in this one, we're not. In Decode, I think we could be, although here we're not really using any registers. So maybe that's all right. In execute, these aren't registers. So we're not writing to any registers and then reading them out here. Is ALU operation. So here in ALU result, we're latching next. Okay. Memory access, we don't have any registers, and write back, we don't have any registers. So maybe it's okay. Let's just add this method here quickly. So have like get working value, which will actually return this ._value1. But if we need access to that, it doesn't seem like we do right now, but yeah, okay, so that's the fix for that problem. Took a little while to implement and debug. It seems my camera's frozen. That is something that seems to happen. I am getting a new computer soon, so hopefully we'll avoid some of these kind of issues in the future. Thank you for watching, and I will see you next time.